Hello everyone. So today we're going to be making a ROM for Lab 4 using Verilog. So let's pull up the document. Okay, yeah, so here it is. So in this lab, we're going to design a Verilog module for a ROM. The ROM needs to be able to hold 32 signed integers, each 8 bits. Thus, must have 5 address lines. And so yeah. So this right here is a traditional ROM. Read-only memory is what it stands for. So there's only going to be 2 inputs. Well, in this ROM, and the number of inputs depends on the number of numbers you're going to store in there. So in this one, there's going to be four values that can be stored in, and the output is 6 bits long. And so if you want to read what's in address 00, put a 0 here, 0 here, and you get 00000001. And if you want to get what's in address 1, 0 here, 1 here, and then that number will display the output. And yeah, it's a purely combinational device, and it's all modeled by this truth table. And we could add another bit. Let's have that be there like that. And we would just add like a whole new column. So yeah, we get to choose the number of outputs in this lab. It's going to be 8. Yeah. Take that real quick. Okay, so yeah, let's say we wanted to build this thing. Oh my. Let's say we wanted to build this ROM. So what we would do is we would get our truth table first, and then get our K-maps, and then we get our equations, and then using that we would be able to build the circuit. So this is the finalized circuit. So for outputs 2 and 1, it's going to be 0, and for the rest of them, it's just modeled by the equation. So yeah, this is a very simple ROM. Oh yeah, that right there. There we go. Okay. So this is ROM in our lab. Even though it says ROM, we're actually making an EEPROM, electrically erasable programmable memory, where we're going to have the same select lines and the same outputs, but we're also going to have all of these other inputs. We're going to have 2 buttons, one for load and one for clear. And then we're going to have switches on the board that are going to be for um, manually setting what value we want to write. So this right here is just a little truth table I made just to kind of model what's going on. So start this bottom one. Whenever clear is high, it does not matter what the rest of the things are. What you're going to see in the output is going to be 00000 all the way to the end. For load, does not for all the addresses, does not matter what the address is. Once you press this load button here, these values that you have set on your switches are going to instantly be reflected here in the LEDs. So if they're all ones, and whatever this is, once you press this load button, they're all going to turn into all ones. And then when none of the buttons are pressed and you're just in a state, it's just going to show the contents. So yeah. Um, Later. Okay, so let's go into Verilog now. Okay, so we're going to create a project. Next, we'll call it EEPROM. Oh, I like to do it NF. You can name it whatever you want. Name the constraint file CF constraint file. Family ARC7 package CSG324, and this one right here. Okay. So we need to think about what our inputs and outputs are going to be. We're going to have how to make this good. Okay, so we're going to have our load. We're going to have our O. Then we're going to have our load button right there. And then we're going to have a clear. And then we're going to have our S right here. Input. And the load, what is that going to be? There are 5 of them. So the way you make them all abbreviated, it's like this. 2 input them buttons. Switches. Next. Alright. So S is obviously going to be to 0. We do have an output. O. It's going to be 5 to 0. And there is going to be one other input. This is just to help give us more flexibility so we can use the clock. Okay. So to start off, because this is memory, we're going to want to have there be registers. Reg. Make sure you make it 5, 0, 1. Then let's do some more. Okay. So these are going to be the registers that store the values that we want to write to the memory. So change this to be 7, 0. Okay. Okay. So this always block here is going to allow us to do some stuff. So a statement. Okay. So pretty much what this case S is going to do is it's going to give us control of what happens for all possible combinations of this. So when S is 0, we're going to want to store information into the first register, and this can come in from the load. So begin reduced if B what am I doing? If load. So we're in state 0, the select line is 0, 0, and we press the load button. Whatever values are going to be, whatever value is going to be right here, are going to be stored in this register permanently. And then if clear, then it's going to store 0, 2, 8, tick. Now for this, you can either do B and then 8 zeros, or you can just do it in hexadecimal and then do 2 zeros. Okay, so now that we have the two cases for if buttons are pressed, what we want to happen all the time is we want to have our O equal to store 0. Oh, yeah, we need to make this a register. Yes, that error went away now. Okay, so yeah, when we're in state 0, all this is going to be happening. You press the button, you press the load button, then all of a sudden these values here will go here. Just move it. So yeah, we're in state 0. We press the load button, all of a sudden all this stuff here is going to transfer here. We press the clear button, all of this is going to be cleared, and the internal register is going to be cleared too. I guess more accurately, when we press load, the values here get transferred into the register, storing it all, which then gets reflected into the output. They're going to be pretty similar. Let's change for these. Oh, my dude, it's 3. Okay. All right, now we need a constraints file. Okay. So we need to map our inputs. Let's make there be these two inputs. Let's map those to be right here. Here, so here and here is we're going to map those two physically. So we want it to be the first two. So I'm going to put 0, 0 in the very first one, this one in the very next one. So we got this taken care of. Now we want to do this input. So instead of doing that one right here, let's move that whole string of inputs to be at the last 8. So 1, 2, 3, 4, 5, 6, 7, 8. And it's L. So change this to be 0. Okay, so we got that mapped, got that mapped. Now we need to map the buttons, so let's go find the button section. We'll need the 7-segment display stuff, we don't need that. And then let's delete everything after too. We only need 2 buttons. We'll make the one that's labeled B and C right there in the middle. Right there in the middle. Let's see. So yeah, you can't see, but the little writing underneath in white, that's it's got the label of it. So if we want to map it to the B and C one, we look here, and then we change that to the name of our button. Our button, we'll make that be our load one. And then the other button, BTNU. So wherever on the board there's a button labeled that, whatever we put here is going to get mapped to that. So clear, put our clear there. So the last thing we need to do is map our output. So O. Okay, so 8 of them. 2, 3, 4, 5, 6, 7, 8. So yeah, these LEDs, the first 8, are all going to be connected to our output now. Once we change to be the right name. Alright, so we've got it all mapped physically, we have our code. So one thing we have to do now is generate the bit stream. Let's hope it works. You're back. Yeah, it always takes a while to run the bitstream. So if you're watching this, you can just skip forward to whenever it loads finally. Oh, it fell. No. Oh, yeah, we forgot to map the clock. Yep. CLC. CLC. Okay. Now it can work. And feel free to just skip ahead to like 2 minutes later in the video for when the bitstream finally generates, because it does take a while. Good time. Okay, it worked. So, it's taking a while. Open our hardware manager. Hardware the device. Okay. So, hold on. So these are going to be our output LEDs, which is going to be this right here, O. O is going to be represented by this. So whatever the 8, so whatever 8-bit value is in there, that's going to be represented by these LEDs. So that's how we mapped in the constraint file. These two inputs for S, it's going to be right here. These two. It's input for load. It's going to be these last 8. And then the load and clear button, it's going to be these two. So right now we are in state 0. So the output, the LEDs are being set to the value stored in store 0, that register that we made. And right now there's nothing because we haven't pressed a button yet to initialize it. So let's set a random value right there with these switches. And then let's press this. So yeah, now what happened is we pressed the load button, which is this middle one, and then all at once the value stored in L0, so it was 111001111. That value got sent to store 0, and then output O got represented of that. If we switch to state 1, it goes away because we're no longer in here now, so now it's showing output O. The LEDs are being output O is showing the value that's in register store 1, which has not been initialized yet. So let's make there be a different. Let's make this one be all ones. And it keeps that. If we go back to state 0 or address 0, it retained the value we last put in. If we go to 1, it has that. Now let's go to 2. Let's load in something else now. Let's load in 11000011, and it reflects that. Go to 11, last address, load in another thing. That goes right there. Okay, so go back to state 0. It kept the value we put in. Same thing with 1, same thing with 2, same thing with 3. And let's say we want to change it. Like we want to change that. So we want to change state 0 to be this new value that we just set randomly like this. So it changed it to that once we press the load button. And when we go back to it, it still keeps it. So yeah, and also there's a clear button, which is right here. We press clear, sets to 0. And we'll do that for all of them. So yeah, let's load that back in, load that same number into all of them. And I guess one way to make it clear is to just set the registers in input L to 0, and then press the load button, and then you load in a bunch. You load in a bunch of zeros. Let me do that again. I don't know if the camera got it. So yeah, we could press clear to set it 0, or we can set all the switches to 0, and then load it in. See, that's one way of doing it. So this is pretty much the output you should be getting for your lab. It probably will look a little different. Or actually, yeah, it will be very different because well, the LEDs are going to be the same. It's 8-bit, and so will this be around the same. But the inputs, remember, for this little simple example I made, we're only storing 4 binary values. There's that one, and that's the first one. Then there's that one. Then there's that one, and then there's that one. And the reason why there's only 4 is because there's only 2 switches. But if you recall from the lab, there's 5, so it's going to be this many switches being used to store that many different values. So you're going to have to modify your code. You could just do it all from scratch using everything in here. Or you can just use the starter code Dr. Morton gave you and just figure it out from there. I would recommend doing that because that can be as short as just 30 minutes if you really know what you're doing. Or 20 minutes even, or 15 minutes if you're good. But yeah, if you want to brute force your way through it and just do it all completely like this, feel free to do that. Yeah, that, and then there's still more stuff to show. Okay, so this right here is essentially what we've made. So we have our 4 register banks, the one for store 0, the one for store 1, the one for store 2, and the one for store 3. And then we have our load, our all of our load switches all kind of feeding in. And let me explain this right here. So how the flip-flop works is whatever value is in here is going to instantly move over here. So if this is a 1 and this is a 0, so like this is a 1 and then this is a 0, this should change to a 1. I mean a 0. So yeah, this moves there. But the thing is, that only happens when there's a clock pulse. There's a pulse in that very instant, whatever's here is going to move here. There has to be a pulse. If it's just a constant 0, no change. So they can be different. There'll be no change. Or if it's just a constant high, there'll be no change. It's only during this time here that the value here goes over there. So yeah, like you have a pulse, it'll change. And that's a lot of, and that plays into why all these AND gates are here. So we want it to be when we press input B, all of these values get loaded in. So and we want it to only load in to one register at a time. We do not want it to load into multiple registers simultaneously. That's what this is. When we're in state 0, 0, we put those two into the AND gate with the inverters there. And then these two things will be 1, 1. And then dependent on what buttons get pressed, that will let the signal propagate through. So we're in cell, like so we're in 0, 0, 0, 0, inverted, 1, 1. Go down here, there's 0, 0. This 0 makes it all the way through. So this can't be loaded. Same thing here. The 0 will get loaded there. So no change will happen here. And here both of them are that way. So no change will happen here. So yeah, this last AND gate with the cell 1 and cell 0 and the inverters, that helps control which one changes depending on the state you're in. Because when you're in state 1, 0, 1, 1 there, 1 there, because it gets inverted. And then for all the other ones, nothing's going to happen. When you have 0, 1, 0 goes in there, so the AND gate can't pass anything. It's just always going to be 0. Like, let's say we're in state 0 for this one. That'll be 1, that'll be 0. Because of this one, the output is always going to be 0 regardless of this third input. And because it's always 0, there will be no change between there and there. Yeah, let's go back to the first one. So we state 0, 0, 0, 0, those two are 1s, so then the change is going to be dependent on this. So this will change depending on whatever that last input is. So right now both of these are 0 when nothing's pressed. The clock is always going up and down, but the output will always be 0 when B and C are 0, which will then keep this 0. But if B is pressed, all of a sudden the value here becomes dependent on the clock pulse and not B. So then the clock pulse makes it through. And then because this is an OR gate right here, it doesn't matter what this is, this goes through too. So then the clock pulse makes it through there. And then it actually makes it through there too. I'm sorry if that's a little confusing, but this is just to show you how to make it at the gate level. So yeah, we press, oh, and then simultaneously while we do that, while it allows for the clock pulse to happen, when C is 0, there'll be a 1 here, so then that doesn't become relevant. And then load 7 is going to be the value. It could be a 0 or 1. And then when B is 1, when it's pressed, the AND gate is going to pass through whatever the load 7 value is. And same thing for all of these. So all at once, these values are going to be put in there, and then it'll shift it over to the other side. And then there's the output multiplexer, which all 8 wires from each thing go into the first one. And then depending on the select, the the, the state we're in or the address, if it's 0, 0, it's going to take all the stuff from the top. If it's 0, 1, it's going to take all the stuff from here and reflect that on the output and so forth. So I have, oh my, I have a simulation of this to a degree. Okay, yeah, so this, okay, so in this example right here is not quite as complicated as this, but the principles are the same. So this value right here, this is like the equivalent of our L. And then this right here, these two, that's the equivalent of our S. And then this is the clear button, and this is the load button. That's going to load whatever is here into the output. So let's set the address to 00. That's this top one. And so we want to load 100 in there. We're going to press our load button. So when we do that, it loads that into there. And then the output is there. And then let's say we want to change the address to display the contents of the second register. So 110 is going to go there when we change the address. And it does that. Now let's say we want to clear the contents in 110, so we press our clear button. Turns to 0. And then the output turns to 0. Let's say we want to go back to address 0. We do that, it displays the contents of the stuff in there. And let's say we want to clear that. Clears. So we want to load in another value. Press the load button, and it loads it. Shows the output. Change the address. Load in a different value. 001. So yeah. Yeah, one. Let's reconnect. So yeah, if anyone wants to simulate this entire thing, feel free to do that. You'll probably get a lot of extra credit for doing that because it'll really be really good to just do that. But I do gotta warn you, the this whole simulation, this website does not have a model for multiplexers that have multiple bits. So you're gonna have to find a different platform to simulate this entire thing on. So yeah, all of this, if you want to simulate this, please do it. That'll be real great. A lot of people who come after can probably learn from this because it'll be a much more complete simulation than this. But yeah, if anyone wants to do that, that would be really great. But you're not going to be able to use this website though because they don't have the multiplexer we need. So I had to do this weird stuff with normal multiplexers. Like here, let me show you guys what they do have a model. Increase the bandwidth. Yeah, they do have this model, but I don't know how I would get a bunch of separate stuff. This is kind of one input, but as you can see, there's three of them. Like, it's just not doing it. Okay, there we go. So yeah, they do have this model that will take in a whole string of values and then display the output. So the thing in address 0 is this, so this is there. This gets passed to there. Yeah, this gets passed to there. And then we change the address to 1, it's going to change this as bottom 1. So yeah, this right here goes there. And that would happen for all the other ones too. So I don't know how to do that though. When you have a bunch of little inputs like that, like you would do this. Yeah, it doesn't work. So there's no way of doing it with individual inputs. It has to be a big thing, but that's bad because I don't know if I could just get a multiplexer that can do this, but use these three together like that instead of it having to be one fixed thing, then I can get a good output, and we could use this software to simulate the entire thing. But nope, that doesn't exist. So yeah, if anyone wants to simulate this entire thing, free to do that. That'd be very helpful. Yeah. So yeah, this is the lab. You're gonna have 5 address lines, and then you're gonna have 8 LEDs showing the output of what's being stored in the address. You have your load button and your clear. And oh yeah, he wants it to be the right button, so you're gonna have to change that in the constraint file. I just kind of used whatever buttons, but yeah, definitely follow the instructions. So yeah, that's it for lab 4. Thank you. Bye.